recording. So we should be recording. Okay, so like I said last week, we're finally getting into the meat, or what I consider the meat of ham radio. And a lot of times you see people refer to the magic in ham radio. And I always kind of cringe a little bit when I hear that, because it's really, there isn't any magic. It's all math and physics. And the better you understand the physics and the math, the better you'll understand what's going on in your station. So that's one thing I try to do is to try to explain, these core um, elements, so you'll have an understanding of what's happening when you get your rig up and going. So I don't know if it helps or not, but we've had such good success with this. I'm pretty confident that I'm not confusing anybody, which is my biggest hope. So we'll go ahead and get started on that. So this is chapter 4. We touched on this in the technician level training, basic electrical concepts. We talk about decibels, RMS, which is root mean square. It's a mathematical calculation, and PEP, peak envelope power of a signal, and that's also can be understood with a little math. We'll get into resistors, capacitors, and inductors. And I think what we got into mostly with the technician course were the resistors, and probably just lightly touched on capacitors and inductors. But we'll get into that in a little more depth, because those are some pretty handy devices to do some things in our circuitry. And then we'll take a look at series and parallel circuits, transformers, and vacuum tubes. Just a comment on vacuum tubes. I got my electrical engineering degree in 1975, and my dad was an old school electrical engineer, and he was appalled that I got that degree without studying vacuum tubes. But even that far back, the transition was there. But the vacuum tubes are still used quite a bit in radio communications and ham radio, particularly in the power amplifiers. So we'll touch on that a little bit. And then we'll get into reactance, impedance, and resonance. All of these are kind of pretty basic concepts to help you understand what's going on in a tuner, in an antenna. They're all using the same tools. Then we'll get into some solid state devices. Well, they're also diodes are also vacuum tubes. So we'll get into diodes, which are nothing more than it's like a check valve in an air hose or a water hose. It'll let current flow in one direction, but not the other. We'll get into a couple different kinds of transistors that are used for amplification, and integrated circuits and microprocessors, and touch a little bit on basic test equipment. So we're going to take a look at the series and parallel circuits. And what we have up here in the top left-hand corner is a series circuit. By series, it means one resistor is connected directly to the next one, and then comes back around and hooks up to the power source, in this case, a battery. So this is a 9-volt battery driving 3 resistors. And there are 2 fundamental laws of electricity that we use to understand what's going on in a series circuit and what's going on in a parallel circuit. And it was first developed by a fellow by the name of Kirchhoff, and it's his voltage law and his current law. And the voltage law, what it says is that in a series circuit, if you go around and measure the voltage across each one of these resistors and add them up, the sum of those voltage drops will equal the source voltage. So that's just a fact, and we can use that relationship to figure out what these resistors are and what kind of current is flowing in them. uh, kind of a companion to Kirchhoff's voltage laws is current law. And that's addressing parallel circuits where the resistors are connected in parallel and back to some voltage source, in this case, a 9-volt battery. And what this is saying, what Kirchhoff is saying is that the current flowing into this node being this area here, is equal to the current that's flowing out. So that, let's say you pump 1 amp this way with this battery, you've got 1 amp going in, and the sum of these three currents is 1 amp. If you add them up, they're 1 amp. Because you can't store current in a node, it has to pass through. And you can think of that in the water analogy. If you had 3 hoses connected in parallel, like these resistors are, whatever's flowing into each of the hose inputs, the sum of those is going to be what the inflowing value is. So with those two relationships, we can understand and figure out what's going on in these. So we'll take a look at those. So Ohm's law is the relationship. It was developed initially by a fellow named Ohm, and he was given the honor of having resistance units named after him. And what he discovered was that if you look at a circuit that has current flowing in it and a voltage and a resistance, there's a relationship between those three values. And the V is the voltage. For example, if you're generating the voltage from a battery, and we refer to V as volts, or sometimes you'll see it referred to as E, which is an abbreviation for electromagnetic force, or EMF. So you may see these three descriptions of voltage, but they're all meaning the same thing. And sometimes people refer to it as a potential difference. Now, in our water analogy, you can think of volts as water pressure, how much energy is available there to move water. So that's kind of the analog in the water example. Then the current is represented by the letter I, and it's measured in amps. And it's what flows through the resistor, the flow of electrons, the flow of charge, actually. So that again, in the water analogy, this would be equivalent to the water flow through a hose. So you have water pressure pushing water, and you get a certain amount of flow depending upon the restriction that you have. And the same thing in this circuit. And then the R is the resistance. It's measured in ohms, which is signified by omega, the Greek letter, a capital omega. And in resistance, you'll see reference to 1 k ohm, which would be 1,000 ohms, or 1 mega ohm, 1 m ohm, that would be 1,000,000 ohms. So what Ohm came up with was a relationship of the voltage, the current, and the resistance, to where if you know any two of these, you can calculate the third one. So if, for example, you know the current and the resistance, his formula is you multiply the current times the resistance and you get the voltage. And this is a little triangle visual aid to help you remember that. If you know the voltage and the resistance, then you can calculate the current, because it's the voltage divided by the resistance, as you see here. And then if you know the want to determine the resistance, and you know the voltage and the current, you can get the resistance by dividing the voltage by the current. And typically, for example, let's say you wanted to know what the resistor value was. You would attach a known voltage battery to the resistor and measure the current flow with a milliamp meter or an ammeter, And then with those two values, the voltage and the current, you can calculate the resistance. Now, this is how my dad taught me Ohm's law back in grade school. And rather than this triangle visual aid, and I could still see it in my mind when he drew it. He drew an eagle, an Indian, and a rabbit. I'd probably get, what do they call it? I don't know what they call it, where they go after you for being politically incorrect. But this is how I remember it. And all you have to do is remember the relationship between these three characters. So if you want the voltage or the E in volts, you just multiply the Indian times the rabbit. The current I is the eagle over the rabbit. And then if you want to calculate the resistance of the rabbit, it's the eagle over the Indian. So even to this day, this is how I remember Ohm's law. Okay, so now looks like I duplicated this slide. This looks awful familiar. Okay, I guess it was just a reminder. We're going to look at the circuit we just looked at back here. I just duplicated it here so I wouldn't have to scroll back like I just did. So what we have here is, and I'm going to go through this more for understanding rather than you actually having to do it, although it's not all that difficult once you understand some of these basic concepts. But in this case, we have, where'd my mouse go? Oh, there it is. We have a 9-volt battery connected in series with 3 resistors, a 100 ohm, a 300 ohm, and a 50 ohm resistor. And in the parallel case, we've got the 9-volt battery hooked up to 3 resistors in parallel, a 90 ohm resistor, a 45 ohm resistor, a 180 ohm resistor. And what we want to find out is what are these voltage drops across these resistors and what is the current flow through each one of these resistors. So we're going to take a look at the parallel circuit first. And if you look at this, just in terms of this battery and this resistor, what we have is we have a current I1, which is the current through resistor 1, and that's equal to the voltage across the resistor divided by the resistor. So we've got a 9-volt battery across this resistor, and it's a 90 ohm resistor, so I1 should be 0.1 amps. And then if we look at this resistor, we've got a similar situation. It's the same 9-volt battery across this resistor. And so I2 is the voltage divided by R2, the second resistor. So that would be 9 volts divided by 45 ohms, or 0.2 amps. And then I've got a typo there. That should be I3. I3, same thing, same look at it. You take the 9 volts divided by the 180 ohms, and that means you have 0.05 amps flowing through here. So you've got 0.1 amp flowing through this resistor, 1 amp flowing through this resistor, or 2.2 amps, I'm sorry, and 0.05 amps flowing through here. Now, if you recall, old man Kirchhoff told us that this current flowing in is equal to the sum of these resistors, so, or currents. So if we want to know what this I total is, we just add those 3 currents, and we add the 0.1 amp plus the 0.2 plus the 0.05 amp, and comes up with a total of 0.35 amps. So if we wanted to calculate the effective resistance of these 3 resistors in parallel, imagine that you're the battery and you're looking down the wire here, and you see 0.35 amps flowing, and you know you're a 9-volt battery. So the total resistance that's connected to you as the battery would be the voltage, which is 9 volts, divided by 0.35 amps, or the combined equivalent resistance of these 3 resistors is 25.5 ohms. So this voltage source couldn't tell the difference whether if you had a 25.7 ohm resistor hooked up to it or 3 resistors of these values hooked up, they will, the same total current will flow out of the battery. So does that make sense?
Oh yeah, we got it.
Okay, okay. This is one thing I don't like about the Zoom meetings is if we were doing this live, I could kind of see how people were following this. Now we go to power, and power is measured in watts. And there was a fellow that I think he actually did the steam generator or the steam engine. He didn't actually invent it; he modified it to make it very useful, and that's why power is named after him now. And for power, a similar diagram here. This is showing you Ohm's law, V over I, E over R, and IR. But for power, the power is always the current times the EMF or voltage. So power is voltage times current. There's a way of measuring power that's described as decibels. And I'll go through this, but you know, unless you're a nerd like I am, you don't need to remember it, I guess. But the way you compute the decibel reading, what it is, it's a measure of a relative power to a reference level. So for decibels of a power ratio, you take the power ratio, the base 10 logarithm of that times 10, which is also equals to, using the voltage ratio, would be 20 times the log of the voltage ratio. Whoops. So if you're comparing the measured power voltage to some reference power, then the decibels can be found by either of these formulas, depending on whether you're measuring power or voltage. Now, there's just some things you need to kind of remember about this rather than formulas. But positive values of decibel means the ratio is greater than 1, or you have gain. And negative values of decibels indicate a ratio less than 1, which means you have attenuation. And well, I guess I just said that. Ratio is greater than 1 can be referred to as gain, and below that's loss or attenuation. The other thing to keep in mind is if you measure the power and you calculate the decibels at a certain level, and if you double the power, the decibel reading goes up 3. So 3 decibels is doubling the power. So that'll, after you work with it a little bit, that may make a little more sense. Let's see, what was this? I forget why I put this in here.
Well, it looks kind of like that. If you go up 3, you double the power thing.
Yeah, that's it. That's it. That's the trouble with just doing this once a year. Right. So you go up 3, and then the power is approximately doubled. From here, if you go up 6 decibels, then it's 4 times the power. So that we'll get into that when we're looking at amplifiers and antennas. Now we get to AC power, and we touched on this in the technician course. AC power, for example, is what you have in your house. That's a 60 hertz sine wave that goes from 0 volts up to let's say 120 volts, comes down to 0, and then it goes to minus 120 volts, and all that's done 60 times a second. Now, the way to measure the power, there are several ways of measuring power on a sine wave like this. This could also be a sine wave for an RF signal, where the frequency would be much higher. But you have several ways of measuring power. Root mean square, RMS, is the formula comes out that you measure or calculate the peak voltage times 0.707, and that's the RMS reading. Now, in your house power wiring, it's referred to as 120 volts AC, and that's what they're referring to is the EMS or RMS value for the power, because your actual peak voltage, I forget what that is, but it would be 1 over 0.707 times the 120. So it's probably up in the 150, 160 range, excuse me, for your peak power. And then there's an average here, which is 0.6386 times your peak value. And you can see that the average power is lower than the RMS power. But typically, when you're looking at power of an AC waveform, you're looking at the RMS value or the peak envelope power, which would be from here to here. So to calculate the average AC power, you need to know what the impedance that's driving, and we'll get into impedance a few slides later, and the RMS voltage. And it's just a matter of Ohm's law and the power equations that you calculate this. So if this is a modulated AM signal, which it is, the peak envelope voltage for the waveform, the peak envelope power would be 0.707 times the volts from peak to peak. Divide that by 2, because if you're going from peak to peak, what you want is from 0 to the peak, and that's why you divide it by 2. And then the peak envelope power would be 0.707 squared divided by R, or the RMS voltage divided by R. And the, whoops, here they gave an example. Peak envelope power is 50 volts. And we're across a 50 ohm load, which is typical for an RF antenna, one type of, or several types of antenna, but that's a common impedance. Then the peak envelope power you can calculate as 50 times 0.707 squared divided by 50, or 25 watts. Any questions on that? I think it'll make more sense when we get into amplifiers and antennas. What we use.
Yeah, so far so good.
Okay.
I've actually had some of this stuff for some of my work courses, so
Okay.
it's a good review, but because some of it's still a little fuzzy.
Okay, well, that's why we're amateurs. I keep reminding everybody we're amateurs. We don't have to be professionals. Okay, now, are you familiar with these schematic symbols?
Yeah, a lot of them.
Okay, yeah, it's I think generally what is attempted in having to make a schematic symbol. Let's say, for example, up here in the resistors is just this little saw blade jag symbol, and that kind of makes sense because resistors can be wound resistor wires, and then they usually try to indicate further action of the resistor by a little symbol in addition to it. Keep losing my mouse. Oh, there it is. So generally, and this goes for most schematic symbols, if the device is a variable device, they'll indicate that with an arrow in some fashion through it. And in this case, for example, this is a photon resistor where they're indicating the light is changing the resistance of the resistor depending on how much light is incident on the resistor. This is an adjustable resistor where with the arrow it's showing that there's a slider that moves up and down on the resistor, so you can change the resistance from here and from here by moving the slider. When they put a little dot there, that means that it's tapped there or physically connected at that point. And they'll use that same kind of symbol on inductors, we'll see in a minute. And then if they're like the sixth one, there's a thermistor, which is a resistor that changes with temperature. They'll indicate that by having a little T temperature symbol there. And then if you look at capacitors, graphically, it's what a capacitor is. It's two parallel plates with a dielectric in between the plates. So that's what's represented with this symbol. I can't even read what that is. Well, here's a variable capacitor. An electrolytic capacitor has a polarity. Most capacitors don't have a polarity. So if it's an electrolytic, they'll indicate that with a plus sign on one side. We'll see those in power supplies. Similar with the inductors. An inductor's a coil of wire with either an air or some other material as a core. And like this top left one would be an air core inductor because there's no indication of anything in the core, it's just a coil of wire. The one to the right's a variable inductor. The one below that would be a variable iron core inductor. So there's kind of a logic that's kind of carried through all the various devices. Then on the right, these are the symbols for vacuum tubes. And you can see that there's usually an anode and a cathode. And if you only had an anode and cathode with no grid in there, that would be a diode. And then if you have a control grid, that would be a triode. And the way that works is that the flow of electrons, the current flow from anode to cathode can be increased or decreased, modulated by the grid voltage. And then you can have, this would be a pentode because it's got 5 elements, has 3 grids, an anode and a cathode. And here's a dual or a twin triode where you've got 2 triodes in the same container, usually glass container, or I've seen ceramic ones too. So it's just a matter of these are wiring symbols. These are different types of switches, and they physically look like the switch they're trying to represent. So this would be a rotary switch that you can move from this position to this position to that, so that whatever's connected to here can be connected here when that rotary arm is in that position. Different types of lamps, the grounds, whether it be earth ground or a chassis ground, integrated circuits. This is an op amp or general amplifier. We'll get into those in a little bit. Different types of relays. An electromagnetic relay, they're still used a lot. All that is an electromagnet that moves to energize us to open and close a set of contacts. So it's just like a hand switch that you could move this between the 2 points. Instead of doing that with your finger, you can energize the coil of the relay, and it'll pull the contact, the wiper arm down to this contact and connect that circuit. different diodes. The diode mentioned a while ago, it's kind of like a check valve. It'll allow current to flow in one direction, but it blocks it from the other. And there are a lot of different kinds of diodes, and they all have little different symbols. Where this one above the diode, come on, mouse. Oh, there he is. This is an LED or light emitting diode. And they represent that by the diode symbol with light, so that when current flow is flowing through the diode, it emits light. This is a thyristor or silicon controlled rectifier that will flow current in this direction as long as it's biased that direction, and you have a gate current that turns it on. So this will actually block current in both directions unless you provide the gate current. You'll see this next configuration of 4 diodes. It's a bridge, and what that's used for is converting AC power to a pulsed AC. So it essentially takes the negative part of the cycle and makes it positive, so that instead of the voltage going below 0, it goes back up above 0. Use that a lot in power supplies and motor controls, at least in industry. I don't know. Well, I guess they might use the motor controls on rotators like that with because what you can do is you can take this SCR and use it in that bridge configuration rather than just a straight diode. And then by controlling that SCR, you can control the DC power coming out to control DC motor. More inductors. We'll talk about transistors in a minute. These are some of the schematic symbols for various transistors. These are digital logic schematic symbols. We'll touch on those in a minute. Batteries. And a battery is multiple cells. A cell is one device that generates a certain amount of voltage, and then to get higher voltages, you'll add multiple cells in series to say to get up to 12 volts or 13 volts for a car battery. And different connectors for power and those types of things. So it's probably more than you really need to know, but that's kind of the range of some of the electrical schematic symbols. So looking at resistors, there are all kinds of resistors for different applications. You have a carbon resistor. You see these a lot on circuit boards. You can have surface mount resistors, inline resistors, where you can have multiple resistors in this pack. This is a variable resistor, so that when you turn this, there's a wiper arm on the resistor that changes the resistance. And this is a wire wound resistor, usually encapsulated in some sort of epoxy or something like that, generally used for higher power applications. And generally speaking, the larger the resistor, the higher the power you can use it for. And symbols again for fixed and variable resistors. And then looking at inductors, we looked at the symbols. It's an inductor's a coil of wire. And this schematic symbol is for an air core, and you can see this is an actual air core inductor. Certain number of coils, nothing in the core other than air. There's a variable resistor, so that the slider can move and change the inductance that the circuit sees. And then this is a symbol for a magnetic or iron core inductor, where this is the iron core and this is the inductor. And you can see that's how these are made. The wires are wrapped around this iron core donut. Capacitors, there's tons of different kinds of capacitors. The fixed capacitor and polarized capacitors, the electrolytic. shown here. And these can be fairly good sized capacitors, and they're used quite a bit in power supplies. And then you can also have variable capacitors. It's kind of hard to see, but this one right here, the way it works is it has these discs, and when you turn the knob, the interweaving of the disc changes the surface area. That's disc to disc on the two inputs. So that changes the capacitance as you turn that knob. If you ever take an old radio apart, like an AM radio in a car, you'll see that in the tuner part of the radio. Okay, so now we're going to get into something a little more abstract, I guess. And what we're going to talk about now is reactance. And what reactance is, it's a resistance to current flow, and it's measured in ohms. And in order to understand this, we have to understand how the inductor behaves at different frequencies of a signal, and how a capacitor behaves at different frequencies of a signal. So if we look at an inductor, and we're down here at 0 hertz, which is DC. If you took just a coil of wire and put a battery on it, it will flow a lot of current, and there won't be much resistance to it. Ideally, or theoretically, it would flow infinite current. So at 0 hertz or DC, the reactance of an inductor is 0. And then as you increase the frequency that you're driving the inductor with, the reactance increases linearly, like this is shown here, and the calculated value is 2 times pi times the frequency times the inductance. So 2 and pi are constants. Pi is 3.14. The inductance is determined by the design of the inductor, and then you multiply those products by the frequency, and you'll have increasing reductance. Now, if you visualize what's going on in that inductor, if we're running an AC circuit, it's passing current in this direction. Then when the voltage reverses, it passes current in the other direction, and it does that back and forth and back and forth. Now, if you recall, when you flow current through a conductor, you generate a magnetic field. And that's what these dashed lines are representing, is that as the current flows, a magnetic field is generated and surrounds that inductor. And then when the voltage switches for the second half of the cycle, that magnetic field collapses and then is built back up in the other pole direction. So say if it started in the north pole direction and we switch the voltage, the magnetic field collapses and then is built back up as a south pole. So let's say you've got a 10 megahertz signal running there. This is going on 10 million times a second. It's building the magnetic field, collapsing, building the opposite field, collapsing. And what that does is it doesn't dissipate energy, but it stores energy. And so it stores it in the north direction, collapses, and it stores it in the south direction. So that's what we mean by the reactance. It's in a resistor. If you pass current through a resistor, the energy is dissipated as heat. But in an inductor, it's just exchanged. It's stored and returned back to the circuit. Stored, returned back. So it'll just it'll consume energy by the storage, but it doesn't dissipate it like a resistor does. So as you increase the frequency, the reactance goes up. It has greater and greater resistance to the current flow of an AC signal. Now we look at the other device that's the companion with the inductor, and that's the capacitor. And it's constructed by 2 parallel plates with some sort of dielectric in between it. The dielectric can be air, or any one of a number of different things, depending on what the purpose of the capacitor is. And if you look at this, if you hooked up a DC battery to a capacitor, you would see an initial inrush of current that would flow and charge up the capacitor to, let's say this is a 9-volt battery, and you connected that 9-volt battery to this capacitor. There will be current flow initially, but it'll decrease as the voltage increases until it reaches the source voltage. And then there'll be no more current flow. So at DC, you get you get transient current flow, but not stable current flow. So it'll charge up and it'll just stay charged and no more currents flowing. So it would be a very high resistance to current flow at a very low frequency. Then as you start increasing this frequency and the voltage is swapped between these plates, say on the first half of the cycle, this will be positive and this will be negative. The AC source comes around and it goes negative. Then the polarity will switch. This plate will become positive and this will be negative. And the faster, the higher frequency you go, the less resistance to that flow you'll have. So the reactance goes down. Because keep in mind, reactance is the resistance to current flow. So in the inductor, we're storing the energy in a magnetic field that's going back and forth from north to south. In a capacitor, we're storing the energy in a electric field as the voltage swings from positive to negative and back to positive. So these plates go positive to negative and then they'll switch again. Again, a 10 megahertz signal, it'll do that 10 million times in a second, and you'll be out here with very low reactance resistance to the current flow. So if you notice, the inductor, as the frequency increases, the reactance increases, and in the capacitor, as the frequency increases, the reactance decreases. So that means if we're clever, we can use those two devices to do some pretty neat things. I think I failed to mention that the formula for the capacitive reactance is 1/2 times pi times the frequency times the capacitance. And just as it was in inductance, 2 pi FL, this is 1/2 pi FC. The pi and the capacitance are all constants for a particular capacitor, and the only thing that you change is the frequency. So keep in mind this relationship. The reactance goes up. On an inductor, as the frequency goes up, the reactance comes down. On a capacitor, as the frequency goes up. And if you calculate the capacitive reactance, you calculate it as a negative number, and the inductive reactance is a positive number. Okay, so if we took a circuit and we had a variable voltage source here in terms of frequency, and we put a resistor in series to an inductor in series to a capacitor, and then come back to the AC source, and we plotted the capacitive inductance, which would be this curve here. Remember, as we increase frequency, the capacitance goes down, and then the inductor, as we increase frequency, the reactance goes up. There's a point where they're equal, and since the inductive reactance is positive, the capacitive reactance is negative, they cancel each other out, and the only thing you have at that point is the resistance. And that point's a real important point for a lot of things that we do in the ham radio, and it's referred to as the resonant point. So the resonant point is the frequency where the inductive capacitance and the capacitive or inductive reactance and the capacitive reactance are equal and cancel each other out. And all you have then is real resistance at that point. Okay, so now we're going to look at resistance. Let me go back and talk about this a little bit. I don't recall if we got into tuning antennas in the technician course. Might have mentioned it in passing, but it generally probably isn't a big thing there. But this concept here is what makes tuning a dipole work. Because what you can do is change the reactive capacitance, capacitive reactance, inductive reactance by changing the length of the dipole and moving this resonant point to whatever frequency you want to operate at. So let's say we're on 40 meters and we want to operate right in the middle of the phone band. And for a general, that would be 7.175 to 7.3. So 25 to, so about 230 or so is where we want the resonant frequency. And we'll get into antennas and explain why. So what we can do is adjust the length of the dipoles to move this resonant point to get it where we want it to be most effective in the band that we're transmitting. So this, we'll come back to this when we get into antennas. But thing I hear a lot is people talking about adjusting their antennas. They say, well, I'm driving my SWR down. And no, you really aren't. What you're doing is you're adjusting the resonant frequency to get it to where it'll operate better. I mean, you really don't adjust the SWR, you move the resonant point to get it where you want it. So this is kind of the physics basis of what we're going to be doing with antennas, and filtering also uses inductive and capacitive reactance for passive filters. So when we get to that, we'll come back and review this again. So let's talk about resistance. Resistance is what actually dissipates the power. And the best description I ever heard of resistance and reactance, the difference was a mug of beer. And what this is saying is that the real power, the resistance, is represented by the actual liquid beer, and the reactance is the foam. So you have to provide enough capacity for both the foam and the beer. But generally, for when you're trying to transfer power, you want the reactance as low as you can get it. So the way you look at the impedance is the combination of the reactance and the real power. And this would be an example of a poor impedance match, where we'd have to have a lot of capacity to only get this amount of beer. But if you had an impedance set up where the reactance is almost zero, you get more of the good stuff. And that's, if you look at it from a resonance standpoint, if you're resonant on the point on your antenna, it's where you don't have much reactance, if any. It's all real power. And then as you move the frequency, then this head on the beer gets bigger and bigger and bigger, and you have less effective radiated power, or less of the good stuff. So that just kind of made sense. I thought that was a good analogy. Fellow I worked with talked about that. So now, based on that, we're going to get into standing wave ratios of an antenna. Now, what a standing wave is it's a measure of the rate, the power that we send to the antenna compared to the reflected power that comes back. And if you're at resonance, that's the point where most of the power that you're sending to the antenna, very little of it bounces back. So that means most of it is radiated into the atmosphere as your signal. But because as the frequency changes, you get more and more reactance, either capacitive or inductive, then you get more and more signal bouncing back and less radiated power coming out of the antenna. So ideally, what you would want to have would be a standing wave ratio of 1 all across the frequency would be theoretically what you'd want. But because of this interaction between the capacitive and inductive reactance and the frequency, you can't get that. Because as you change the frequency, on this side, the capacitive reactance becomes dominant. And when you go higher in frequency, the inductive reactance becomes dominant, and it forces reflection of the energy you're trying to transmit back to the transceiver. So this is what you'll see if you do a frequency sweep of an antenna and you're measuring the standing wave ratio. Now what happens, I talked a little bit ago about tuning the antenna, and what you're doing there is you're taking that resonant point by making the antenna longer or shorter and moving that resonant point up or down the frequency spectrum, but you're still going to have that U shape as you get away from the new resonant frequency. And ideally, you'd like to have an actual antenna with a standing wave ratio, say less than 2, through the whole band. Some bands you can do that with some antennas, and some bands you can't. We'll get into that a little later too. But keep in mind, this whole thing is based on the response of the capacitive and inductive reactance to the changes of frequency. Specifically on a diode, we'll take a little closer look at that. We saw the symbol, which was the arrow with the line, and it's kind of indicating a check valve, where the anode is this side, that's the plus. So if you have a positive voltage here and a negative voltage here, you'll flow current. There's generally a voltage drop over the diode when it's forward biased and passing current. For germanium diodes, it's about 0.3 volts. For silicon diodes, it's about 0.7. So that'll have some, we'll get into that possibly at some other point. But it passes current in one direction, blocks it in the other, and it's kind of like a check valve. Mentioned earlier, all kinds of diodes. This is light emitting diodes. There's Schottky diodes, Shockley diodes, Zener diodes, tunnel diodes, just all kinds of them, all kinds of different packages. This is the kind of diode you'll see on a circuit board. Let's see, but it's the package. I'm just trying to look. I really don't see the type of diode I was looking for. Oh well. But there's just a lot of different kinds of diodes in different packages. Now, transistors, we've got two basic types of transistors to deal with for the general. The first type is called a bipolar junction transistor, or BJT. And what a BJT does is it's a current amplifier. So that if you inject a current into the base of this transistor, then the collector current will be a multiple of that base current. It's typically of a transistor, the gain's referred to as a beta, Greek letter beta. So let's say the beta is 100. If you put 1 millivolt or 1 milliamp flowing into the base of the transistor, the collector current would be 100 milliamps. And then because of Kirchhoff's current law, this would be the emitter current would flow here. That's what the E stands for. Then you'd have 101 milliamps flowing through the emitter. So this is the base, the collector, and the emitter. And it's a device called an NPN transistor, which means it's made with 3 layers of negative, then positive, then negative doped semiconductor. And the way I remember which symbol it is I see this arrow here on the left. The arrow's not pointing in, so I use that to remind me that would be an NPN transistor. And then a PNP, where if the dope materials are reversed, its arrow's pointing in. So the thing to keep in mind, it's a current amplifier. And you can see, you'll find transistors in a lot of different types of packages, very small ones, the metal cans like this. This is typically a power transistor, and the purpose of it being in a metal case like that, and also this packaging where the transistor's mounted in this ceramic container, is the idea is that you bolt these packages to some sort of heat sink to help dissipate power. And there's usually a substance, a grease type substance that's electrically insulating but thermally conductive that you put between the device and the heat sink. So transistors going to look like that, and a lot of other ways too. The other type of transistor that we need to consider is called a field effect transistor, or an FET. So we've got the BJT, bipolar junction transistor, and the FET, a field effect transistor. And the big difference between this and the BJT is that this transistor is a voltage amplifier. So what it does, it has 3 leads, a basic FET. This is called an N-channel FET, where it has a gate that you apply a voltage rather than a current. And as you increase the voltage, you can change the resistance of this transistor, which changes the current flow. And you have an N-channel JFET, junction field effect transistor, and a P-channel JFET. And that is the type of semiconductor material that's doped either positively or negatively. And what happens, the reason this controls the current that can flow through here, as you apply the gate voltage, what happens is around this N material in a this would be an NPN, make sure I'm right there. No, it's a P channel. That it's got a P right there in the channel. As you apply a voltage to the N material, there's it restricts and becomes a smaller. There's a field here that restricts the path for the current flow and changes the resistor. So it's called a valve transistor because it kind of acts as a valve. A valve being a triode vacuum tube. So it's very similar in function to a triode vacuum tube. Just remember, it's a voltage amplifier, and the BJT is a current amplifier. And then the vacuum tubes, you've probably seen these. They generally have a heated element so that they can generate electrons that can be flowing from the cathode to the plate. And then the control grid either assists or restricts the flow of electrons so that small changes here are seen as large changes here. And that's the same thing you see on the field effect transistor. Another device you'll see, and this is primarily in analog applications and usually lower frequency, like in the audio circuits and applications like that. But it's called an operational amplifier, and it's usually biased by a plus and a minus of power supply, and the output, depending upon what kind of circuitry you design around it, will be some gain function of the input coming in. So it can be used as a voltage amplifier, power amplifier, by using inductors or capacitors, usually capacitors. In the feedback circuit, you can make this into a filter, and we'll get into that when we get into filters a little bit. But this is a pretty common tool that you use. In fact, it's been around so long, I even used these things, studied them in school, used them when I was doing design work. It's a pretty neat little gadgets. Then you'll run across digital logic gates, and this is the symbol for an AND gate. And what this means, an AND gate means that in order to get the output to go from 0 to 1 or from false to true, both A and B have to be at 1, and then you get the 1 output. That's what this little truth table shows you. There are 2 inputs, so there are 4 combinations of outputs. So for an AND gate, if both A and B are 0, the output's 0. If A is 0 and B is 1, the output's still 0. A is 1, B is 0, it's 0. And the only way you get a 1 output is if both of them are on. Electrically or logically, this is the same as 2 switches in series. If you put 2 switches in series and connect it to a light bulb, both of the switches have to be closed in order to turn on the light bulb. And the OR gate is this symbol, and the output is A or B. And what that says is that if both inputs are 0, the outputs are 0. But if any input is 1 or both inputs are 1, the outputs are 1. So this would be like 2 switches in parallel that are hooked up to a light bulb. Either one or both of them closed will turn the light bulb on. NOT is just an inversion. Whatever A is, the output is not A. So if A is 0, then not A is 1. If A is 1, not A is 0. And it's just a device for switching, inverting the logic. So you'll probably see some of those if you look at some schematics. We'll take a look at rectifier circuits and where you might see these. This is a fairly typical linear power supply design where you have AC voltage. It could be 120 volts, but there will be a step down transformer usually to get it down in the 12, 20 volt range. And if you recall, we looked at a bridge a schematic symbol that was 4 diodes connected in a particular way. And the way the bridge works is that when this is positive, the current flows through this diode, and it's blocked by this diode. So that would be this right here going positive. When this is positive, then the current, or negative, then the current flows through this diode and is blocked by that diode, and that's what gives us this second hump. If we didn't have the bridge in there, the AC signal would have just be what we're used to seeing. So this takes a positive and negative AC signal and converts it to a pulsed AC signal, always being positive in this case. Now, where the current goes then is to a smoothing capacitor. And what this does is it will absorb the current flow build up an electric field in the capacitor, and it'll come up to the peak. So during this part of the cycle, the capacitor will charge to this, caused by this pulse from the bridge rectifier. And then when the voltage goes below the voltage output of the bridge rectifier, then the capacitor will slowly discharge until the next cycle. Need to get my mouse back. So it'll come up, and then this is when it discharges. It's not being charged at this time because the voltage is below that, and the load is pulling current from that capacitor. And then the next cycle comes in, and then it discharges. And this is why we use the diode bridge to take that AC and convert it to pulse DC. If we only used one diode, all we would have, we'd have this pulse, this one would be blocked, and then this pulse, and then that means that discharge time would be much greater, and it wouldn't have as good a regulating capability for the voltage. And this is the, you'll hear mention of ripple on a power supply, and that's what this is. It's the charging and discharging of this capacitor, the smoothing capacitor, due to the power consumption of the load, whether it's a resistor or a radio. These smoothing capacitors are generally very big. You can reduce ripple by making the capacitor larger in terms of microfarads, and it'll make the discharge slower. But at some point, you reach the point that it's not economically feasible, or doesn't make sense, because you can live with a certain amount of ripple. So the designer of the power supply will use the specification for the amount of ripple to size this capacitor based on the type of load that's going to be there. A safety note with this type of power supply, these capacitors can remain charged even when you turn this off. So generally there's a discharge resistor in the circuit that has a much longer time constant. So say over several seconds or maybe even a minute, it'll discharge that capacitor. So if you happen to need to open up a power supply, shut it off, disconnect it, and wait a while. You might even want to check the voltage on that big electrolytic capacitor to make sure it's discharged, or you can get bit pretty well. So that's a very basic power supply circuit, a linear power supply. The other type of power supply that you'll see that we use is a switching power supply. And what it does is it uses a bipolar junction transistor or field effect transistor that'll take the input voltage and it'll burst on and off to maintain the output voltage. And because this frequency is generally higher than the 60 hertz, you don't need as large of a capacitor as you do in the linear power supply. The other problem, though, there are no perfect answers. Engineering is all about evaluating trade-offs. One of the trade-offs here with this type of design, because this switching frequency is high, it can generate noise that can be picked up in the radio unless the design engineer does some things to take care of that. So it has the advantage of smaller capacitor, smaller transformer to drive the same load. So that's a switching power supply. The power supplies I use for my VHF, UHF base rigs and my HF base rigs are switching power supplies, and I buy Kenwood because found them to be very good on this noise problem. So that's just my opinion. Okay, now the schematic part of the test, what they're going to be doing is they're going to be presenting you with a schematic diagram of some sort. And I think there's 2 or 3 different diagrams. So you're going to have to understand the what the symbols are in each of them, and they're in your book. But for example, this is figure G7-1, and it's used for the questions here from A09 to A13. So 4 questions that they could ask, and you'll probably see one of the schematics, and maybe a couple, 2 to 3 questions maybe of identifying the components. So we take a look here, and we look at this schematic, and the question is, what represents a field effect transistor? And so first thing we look at is there's 2 transistors there, and they're different. So one's probably a BJT and one's an FET, field effect transistor, bipolar junction transistor. So if we look at them, just because you've studied, you know that this is a field effect transistor, which is what they're asking about. So the answer would be C. Number 1, that's a field effect transistor. This is a bipolar junction transistor. And you can tell by that kind of represents the drain in the transistor. So it's just recognizing the difference of the 2. Which signals a Zener diode? We didn't talk about Zener diodes, but we've got a, I'm not even sure what that is. It looks like a diode in series with a capacitor. I'm not sure. I'd have to go look that up. I'm not sure what that symbol is. But a Zener diode is this symbol. It's got the 2 little arms on it. And what a Zener diode does is, if you reverse bias it, it won't pass current until you get to the point that you reach what's called the Zener voltage, and then it'll pass current to maintain that Zener voltage. So let's say this is a 7-volt Zener, and we're providing, say, 8 volts here. What you'll have here then is 7 volts, because if this voltage tries to go higher, the Zener diode will pass the current and bring the voltage down to its Zener level. So Zener diode can be used as a cheap, simple voltage regulator if you don't need a lot of precision in a circuit. So that's a Zener diode with the little arms on it there. So that would be symbol 5, D. Yep, we lucked out. Okay, which symbol in figure G7-1 represents an NPN junction transistor? So we know that that's a field effect transistor. So this is a bipolar junction transistor. Number 2, B, and yep, that's what it is. So it's just a matter, you really don't have to know all these symbols, just the ones they ask the questions about. But it wouldn't hurt to know what all the symbols are, particularly if you want to at some point get into looking at circuits and how things work. And then the 12th, multiple winding transformer. Okay, a transformer has an input, a primary, and a secondary, and that's what we have here. We have 2 windings with an iron core, and this is a step-down transformer because the primary has more windings than the secondary. So this is going from a higher voltage to a lower voltage. So it would be 6, which is C, and yep, that's it. And then a tapped inductor, okay? So we know an inductor looks like a coil of wire, and we've got a couple of those here, but we know that's a transformer. So here's the inductor. and it is showing a tap in the inductor by that little dot. So that would be 7A, and that's it. So what you need to do is the schematics that they have, at least know what the symbols are of the ones they're going to ask you about. So because if it's not in the question pool, it won't be on your test. But they will put a subset of the question pool on your test. So that's about all I know. You got any questions, ideas? Anything like that?
I have a couple questions, but don't really relate to much of this.
Well, that's okay. We can go ahead and do them. I'll leave them on
Alrighty.
the video because somebody else may have them too.
Well, I have, for instance, my HT can hook onto the internet. What's the easiest way to find node information near me?
There are a bunch of websites. Let me get going here. I'll pop this up.
I figured there were, but you know.
Oh yeah, there's probably too many. I'll show you the ones I refer to anyway. Here's my ham radio bookmark folder. I don't remember much, but I remember where I put stuff, so I can go find out.
There you go.
Okay, now where would I have that? Repeaters, imagine that. The one I use the most, although I really haven't used it lately. Which one is it?
Yeah, because internet's like cheating for you. I get that.
Well, no, I just don't use VHF and UHF very much. This is one that I use, Repeater Book.
Okay.
Actually, I think the only one I do use as infrequently as I use it. So I'll log in. Okay, and what this has, it has all kinds of stuff. But here are North American repeaters. So I'll go there. And then you can select, particularly if you travel, this is handy because you can go to different states. And I'll select
Right.
Pennsylvania. And then you can select by band. So let's say, let's go to 70 centimeters, see if the Treasure Lake repeater, they've caught that yet. So we'll go to 70 centimeters and let's sort it by county. Oh, for sure, I could sort that by county. So they found 353 repeaters in Pennsylvania, UHF repeaters. Oh, come on. Maybe what I do is I copy and paste this into Excel and then I'll
There you go.
sort by county. But let's see.
There you go.
Let's go see if we can find a Clearfield. If you see one, tell me to whoa, because I'll probably zip right past it.
Clearfield.
Okay.
There you are, right there.
Yeah, there we are. So this is a Treasure Lake repeater.
Right.
And not sure what that means. That's not. Oh, they're showing us not on the air. Let's see what this shows us. 442.525. Okay, so it shows the receive, transmit frequency, the offset,
Right.
The tone, who's the trustee, and it shows where it's
Okay,
at.
now,
Pretty close.
all right, so now on that list, how do I tell which ones are internet based for my, I think it's called wires?
Let's go back. What you may have to do is, like if it's a repeater that's operated by a club, that'll be shown. By the call. We should
Okay.
probably, this is Jim Whitehead's call. We weren't organized enough. He just filled out the paperwork, so he was the trustee. And generally, well, let's go to see if we can find what's a repeater that locally is hooked up to the internet.
I don't know. That's what I'm wondering. How do what's the easiest way to find that information?
390 might be, or it used to be Clearfield. Oh, this is VHF. Let's go back to UHF.
So that one you just had the wires.
Yeah.
Is that what I'm looking for?
Well, that could be. It may be.
Wide coverage internet repeater enhancement. Is that right there?
I'm missing it so far. Do I go north, south, east, or west?
Okay. Well, what I'm saying is, if you look over here at 23
Here's
centimeters and come right down, yeah, that.
Okay, so let's try wires. See what that gets us. Okay, and I think
Okay, Echo Link and all. Okay, so Echo Link and wires is all internet stuff.
yeah.
Okay, got it.
But you could go to these websites, whoever's the trustee,
Right.
you have that kind of information there. But I would think this repeaterbook.com
Okay.
will take care of everything you want to do.
Yeah.
Because you have to kind of, whittle it down from such a big
Right.
mob of repeaters.
Right. Okay. But then, see, now those internet connected ones, basically, if you had the right stuff, you could almost DX off those, right?
Yeah.
Okay.
I remember when I first started, I would get on the 390 repeater, and I don't know if it was wires or something else, but they were tied into the internet, and we'd hear guys from England or Germany or California every once in a while. So yeah, you can go all over the place with that. There are so many ways to do that.
With my little HT, I could DX. That's cool. That is kind of cool right there.
Yeah, right. Yeah, I think that's a perfect what I call recreational ham activity. There's no problem using the internet because you're not going to depend on it in an emergency. You just have fun with it.
Right.
So I don't know why guys get all puffed up over people using the internet. It's just fun. Yeah. Bunch of grouchy old men.
There you go.
Okay, so you got that link then?
Another question I had.
Sure.
Was I got my ARRL magazine, which I'll probably get a subscription. But anyhow, the article in there was you basically make a little 2-meter antenna, and it was talking about dealing with the SWR. So my question is what's the cheapest, easiest way to check how good your SWR is? I mean, I got a little power bar on my HT. Would that just be the easiest way to do it? Just use the thing and see where the power bar goes, or?
You really need an SWR meter. Now,
right.
Mike Smith has one, a portable one. Do you know Mike?
No, I don't think so.
His call sign's W3NV, and he's probably crazier about ham radio than I am. And he'd be more than willing to give you a hand on that. If you want to send him an email. Let me see what his email is. Hold on just a second here. Okay. Easiest way to get it is I'll just,
There you go.
there he is, w3nv@comcast.net. Tell him you're working on the general and ask him a question. Tell him you can tell him I suggested he get a hold of you.
Alrighty, sounds good.
I call him Mr. Haney because he buys old ham equipment all over the place. I don't know if you're old enough to remember Mr. Haney on Green Acres,
Oh yeah, vaguely.
but that's he's really got a lot of stuff. Really is I wouldn't say a fanatic, but a real strong proponent of it. All this stuff.
Nice. All right, I think those are all my questions I had today.
Okay, good. Well, I'll post the. It takes a while for this video to process, both for Zoom and YouTube. So I'll send you guys an email with the slides and the questions and a link to this video on YouTube. So I'm going to stop.
All right, sounds
the,
good.
recording. So we'll see you next week, I guess.
Alrighty, thank you.
Okay, take care.